Hello everyone. My name is Anvita Prasad and I'm from Engineering Physics third year in IIT Roorkee. And today I'll be talking about optical sensors as a part of our course PHN 310 Applied Instrumentation. So before I start talking about optical sensors, let us give a quick review of what sensors really are. So sensors are in our day-to-day environment. We are surrounded by sensors in literally every part of our life. So a sensor is used to detect a change in the environment. And if we use a sensor in conjunction with a signal conditioning unit and other parts, we can use this system to measure any physical property or any change in the environment. So a sensor plus signal conditioning unit plus an actuator that is not necessary, but yes, a combination of essentially these three elements along with other parts forms a transducer. So a transducer converts one form of energy to another, and usually it's other forms of energy to electrical energy because that is something which we can easily detect and quantify. Now, in case of optical sensors, as the name suggests, we use light. So light has a lot of properties which we can, physical properties which we can exploit to be used as a sensor and for detection. So what are these properties? One is, of course, wavelength of light. And wavelength, as you know, is related to the refractive index of a material. So if the refractive index of the material changes, then there's a change in the wavelength of light. And that basically, if the light is in an environment where there happens to be a change in the wavelength and we can detect that, so that can be used as a sensor. Then there's polarization of light. Polarization is basically the direction of oscillation of the electric uh, field vectors. This is, of course, while considering light as an electromagnetic wave. And if we consider light's particle nature, that is, light is made up of photons, then we can also use intensity of light as a property for detection. So intensity of light is basically the number of photons incident per unit area per unit time. Uh, we can also uh, basically uh, have photons incident on a material, causing transition between energy levels. And this transition between energy levels leads to emission of light with a property different from the original light source. So the property can be, for example, say wavelength. Then we can also detect the absence or presence of an object by observing a change in the intensity of light after which is emitted after excitation with higher energy photons. So basically, light, as you know, has a dual nature. So it can have a particle nature or it can have wave nature. So if we consider light as an electromagnetic wave, we can have properties such as polarization or amplitude or frequency, and this is what we exploit using fiber optics, which we will see later in this presentation. We can also consider light's particle nature, that is, light made up of photons, and this can also be exploited using laser diodes or other such devices. So light can be used for contactless detection, counting, or positioning of paths by simple obstruction. So if we have light incident on an object and then we obstruct the light, and can be considered as uh, that can be considered as detection, or we can use it for counting. So one example of this is the optocoupler, wherein we have an LED, and on obstructing the light incident from the LED, this obstruction is converted into an electrical signal which is detected, and we can use this for counting purposes. Now let us talk about some conventional types of optical sensors, which I'm sure you've all heard about. So one is photoresistors. Photoresistors is basically where the resistance of the material varies with the intensity of light. So for example, light dependent resistance. That's basically a photoresistor, which you can see here. So yeah, this is a photoresistor. And next is the phototransistor. So phototransistor is like a typical transistor with your collector, base, and emitter. But here, instead of a current, we are basically providing light energy to the base, and that creates or generates electron hole pairs, which in turn gives an amplified current as the output. So this is your phototransistor. And so this can be used for, I mean, essentially it's very photosensitive, and we can use it for detecting light and other such things. Then you have LED and laser. Now these are not really sensors, they are basically light sources. We are using them to generate light, and that in turn can be used in a sensor, which we will see later. So LED is your light emitting diode, and laser is laser amplification by stimulated emission of radiation. So in a laser, what you have is essentially this is a basic demonstration of how a laser works. So you have a photon incident on an atom, which is in an excited state, and this photon causes the atom to go from excited to ground state. And in this transition, another photon is released. So at the end of this whole process, you have two photons, and you have amplified light. From one photon, you've gone to two photons. This lasing action can be achieved in a PN junction, and then it is called a laser diode. So these were your conventional types of sensors. Next, we'll talk about fiber optic sensors, which are much more in use nowadays and are very useful for reasons which we'll see later. So I'm sure you would have heard about a fiber optic cable. Basically, you have two materials. Uh, on the outside, you have a material made of lower refractive index, and on the inside, that is the core, it's made of higher refractive index. So using the phenomenon of total internal reflection, light, which is incident from one end, will reflect completely due to total internal reflection, and will go on reflecting until it reaches the end. So this is how light is transmitted. And because it's total internal reflection, 100% reflection occurs, there is no loss of light. And that is pretty much one of the major advantages of fiber optic cable. So now, how can we use this as a sensor? So optical fiber can be used in two modes. One is where the fiber itself acts as a sensing element. So for example, we can detect or measure current by the rotation of plane of polarized light, or we can measure strain by phase modulation. So basically, the light which is traveling through the fiber optic has different properties. Here, light is considered to act as an electromagnetic wave, and so there are different properties which changes in which can be detected, and therefore it acts as a sensor. Second is where the fiber is simply used to transmit the light to the transducer, and it returns a modulated signal which is carrying the measurement information. So here you can see a block diagram of the fiber optic sensor where you have a source, which is usually an optical source. So it can be an LED or a laser. Then you have a transducer, which is with a measurement, that is the uh, change in environment that you want to measure. And then this converts it into a signal, say an electrical signal, which gets transmitted to the detector. So as I mentioned earlier, in an optical fiber, we are exploiting the electromagnetic wave nature of light. And so the properties that can be modulated are amplitude, phase, frequency, and state of polarization. Now, there are two types of fiber optic sensors. One is your intensity modulated. So as the name suggests, here we are using the fact that light intensity varies when exposed to a changing environment, and that variation in light intensity is proportional to what we want to measure, the property that we want to measure, and that can be detected by sensors. So the concepts associated with intensity modulation include transmission, reflection, and microbending. Second is phase modulated fiber optic sensor. So again, as the name suggests, here what we are using is the change in the phase of the light. So what we do is we use an interferometer to split the light from a coherent source into two fibers. So one is your reference fiber and the other is a sensing fiber. The sensing fiber is exposed to a changing environment, and that change in the environment causes a phase difference or a phase shift to occur. So now there's a phase difference between the light in the sensing fiber and the light in the reference fiber, and this phase shift is detected by the by an instrument. There are various other ways of classifying fiber optic sensors, but we will not be going into that right now. So, what are the advantages of optical fiber sensors and why are they preferred over other sensors? So, there are many advantages. One is that it's lightweight. Second is low attenuation, that is because of total internal reflection. Third, and a very important advantage, is that we can transmit light over a long distance using optical fibers. So it can be used in remote sensing applications because when we have light incident at one end of the optical fiber, and I can use that light to sense or detect something at the other end, and the other end is say miles away. So very useful for remote sensing. It can withstand extreme conditions. It also provides greater flexibility, and it is immune to electromagnetic interference. Some disadvantages are, of course, high cost and unfamiliarity with the user. But the advantages are sometimes uh, definitely outweigh the disadvantages and therefore are still very much in use and popular in various applications. So now let us look at some applications of optical sensors in daily life. So one I'm sure you've all seen is the ambient light sensor. This is a small dot which you can see at the top right corner of your phone. So this is your ambient light sensor, which detects the change in light or intensity of light in the environment and accordingly changes the brightness of your screen to conserve power. Next is the contactless sanitizer dispenser. This has become very popular during COVID times. So basically, the sensor detects the presence or absence of uh, an object underneath the dispenser using an optical sensor. And when an object is detected, the dispenser is activated to release the liquid or the sanitizer. Third is using an optical sensor to detect liquid levels. Or here, what we use is an LED and along with a light transistor. And basically, the idea here is that when light is emitted by the LED into the environment, then depending on the environment particles will reflect back the light. So if it's air, there will be less dispersion and most of the light will get reflected back to the transistor. But if it's some liquid, then there will be some dispersion of the light and less light or less amount of light is reflected back to the transistor. So depending on the intensity of light which is detected uh, at the transistor after reflection, we can determine the level of the liquid. Now talking about applications in robotics. Now robotics uses a lot of sensors of different kinds. And here I'll be talking about one specific application, that is the robotic hand. So this research was done by a team, uh, and I have attached the source here for you to go through. So basically, they developed a robotic hand and they used fiber optics to embed 14 strain sensors into each of the fingers. So this gave the hand the ability to determine where its fingertips are in contact and to detect forces less than a tenth of a Newton. So using fiber optics to create so many sensors was able to increase its sensitivity. Now, adding conventional pressure or force sensors here is problematic because wiring can be complicated, prone to breaking, and susceptible to interference from electric motors and other electromagnetic devices. Now, the hand that was developed here, the robotic hand, incorporates commercially available fiber Bragg grating sensors, which detect strain by measuring shifts in the wavelength of light reflected by the optical fiber. Now, the problem with this particular robotic hand was that it was not as flexible as they wanted it to be. So the same team developed a highly stretchable and flexible optical sensor using a combination of commercially available silicon rubber materials. So here, what they used were soft waveguides, which are essentially like your fiber optic cables. So soft waveguides lined with reflective gold, and so these waveguides were lined with reflective gold, and uh, cracks developed in the reflective layer, allowing light to escape. So depending on the amount of light that is lost through those cracks, strain or other deformations can be calculated. So these are some of the resources which I've referred to. In conclusion, all I would like to say is that optical sensors are everywhere around us, and they have a wide variety of applications because light has a variety of properties which can be exploited. And that's all. Thank you.